You what? It's been 2 months since we made our last video? How'd that happen? Oh, Nan, you left the telly on all night. I wonder what sort of stuff they stick on the telly during the day. The following programme may cause brain damage. Can't be that bad, can it? Ah! Where's the controller?
And I'm like, well, for the number 2, we can do it in a red bag.
Nan! Where's the controller?
A cool breeze.
I'm wearing this for scientific reasons.
Quick, Nan! I can feel my brain being damaged!
Yeah.
You describe yourself as an angel communicator.
Yeah, well, Angel, yeah.
Nan! Just bludgeon me unconscious!
Wee Willy Winky sausages.
Ah! Oh yeah, I remember now. Still, can't be angry at Nan. She did save what's left of my brain, didn't she? Well, what were we doing? Oh yeah, we were making a supercomputer, weren't we? Let's get back to doing that. Last time, we made all this, didn't we? All this inbound circuit here. So I reckon what we should do is add up all the propagation delays and see if it's fast enough.
I don't think so. No, 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 no. I don't think so. No, 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 no. It's never, ever, 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 ever gonna happen. I don't think so. No, 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 no. I don't think so. No, 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 no. It's never, ever, 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 ever gonna happen. I don't think so. No, 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 no. Maybe someday you'll have it your way. Maybe someday it'll all work out.
Oh. It's not fast enough, is it? No. Huberman, we're going to have to take it apart and redesign it, because, well, yeah, ain't going to work, is it? Well, go on then, Human Man. You start taking it apart, and I'll work on the circuit. Just in case you don't know what propagation delay is, basically, it just means if you change the input, the output, well, it don't change instantly, do it? There is a delay, and that's it. We've done an explanation. Weren't that exciting? Human Man, get rid of all them pull-ups first. Yeah, that's it, them things. The Human Man, well, he's getting rid of these because they slow the circuit down. But the biggest problem with this circuit is that we're doing things one after the other. So if we have a look at it, when the control register is clocked, all the stuff from this side, well, that transfers to this side. And that takes time. And then we decode the control register. And then we use our pattern matcher to determine if this message is intended for this computer. Now, it would save a lot of time if we could decode the control register and determine whether the message is for this computer at the same time, rather than doing them one after the other. It would also give us more decoding time if we looked at this side of the register rather than this side. So we're decoding stuff before we actually even need it. I think people that are smarter than me probably call that a pipeline, but I don't really know. So I'm staying away from all them big fancy words. Now, our only problem is that we need to see if the physical address of this computer is equal to the destination register, and at the same time, if the pattern register is equal to the destination register. So that means we're going to need another pattern matcher. But this second pattern matcher that don't got to be as fancy as the first one we made. In fact, this second pattern matcher can be done using just one chip. We're going to be using the 74HC688, which is an 8-bit comparator. Basically, it has a look at two 8-bit numbers and tells you if they're the same. So, let's have a look at that on a schematic. There we are. There's our pattern matcher from before. It's a different shape now, but the same bits are all there. And here's the 74HC688. And oh look, there's another 74HC688. But that's for something different. We don't need to know about that just yet. Just pretend that one don't exist. Now what you need to do is get rid of the address switch, because we'll put that on a separate board. Now what you need to do is tie all them chip enables to ground. Human man, remove them wires there. Yeah, them pink ones. Yeah, that's it. Now, you see them purple wires there? Human man, point to the purple wires. Yep, that's it, human man. You've got to move them from that flip-flop over there to that flip-flop over there. Yeah, that's it. You got it, human man. Well, what we'll do, because you don't want to sit there watching someone sticking wires in breadboards, we'll just come back when the human man's finished it. Alright? Oh, right, you done, are you, human man? Well, I suppose you better start doing the address board, ain't ya? See, the human man's already done the power and ground for both rails. Well, get the dip switch, human man, stick that on there. And the pull down. And now ground for the pull down. And the other end of the dip switch, well, we're going to make all them high. Human man, get them two 748C688s. Well, stick them on there then. The human man is just going to wire it up. And then we'll come back when he's finished. So, I seem to have lost a bunch of footage, but here's a still from later on in the video. And as you can see, there's lots of happy little wires. Right, human man, you're going to have to detach the pattern matcher from the old control register decoding circuit. Human man, this D-type flip-flop here, the one that was on the old decoding board, well, you need to find a new home for that, don't you? Yeah, that one. Yeah, that'll do. Just there. There we are. The human man's done it. I suppose he'd better test it now, hadn't he? Right, human man. So, set the destination to the same as the address switch. That's right, human man. All zeros. And look! It worked! Change it. And it don't work. Change the switch. And it works. Look at that, human man. I suppose you better just check to make sure the pattern matcher still works. Yeah, that stuff there. So, as before, load the pattern register. And the human man's loaded that with all zeros. Now, human man, load the don't care register with all ones. Right, now change the destination. And look at that! It's working! So now we just need to work on the decoder bit. And then somehow combine that with the signals from our pattern matchers. And then get it to save the conveyor belt into the inbound buffer. So the first idea I come up with was using a 74HC138. And that's to do the decoding, and then, along with the signals from the pattern matchers, well, they all get bunged into an 8-bit latch, and then we use them results to do a bit more decoding afterwards. But the problem with this is it's still too slow. What we really need to do is do all of our decoding on the left hand side of the latch. So my second idea was to use these 74HC151s, and these are 8-to-1 multiplexers. But I couldn't figure out how to get it to work, so yeah, gave up with that idea. Eventually I settled on two ideas. One is using a 64K ROM, and the other one is basically the first idea I had, but sticking all the stuff on the left hand side of the latch. Both of these circuits have their pros and cons. You know, if only there was a way we could do both at the same time. Now, the decoder circuit we're going to talk about here is really simple. Out basically, as you can see, as a decoder circuit, all you do is bung all your control signals on the address lines, as you can see, and then your decoded control signals by this on the data bus. 74HC139. I know what you're thinking. You're thinking, but we've changed that for a 74HC address lines there. So there's 16 control signals. A 3 to 8 decoder. You only told us about 4. Why have we done that in the last video? Well, we don't need the extra outputs. The 4 I told you about in the last video, we didn't actually use the first 4. BF in, DM, what we needed AD, was the extra inputs. Well, so we actually called in empty low 2 in the last video. We've put in empty full in. So I changed it to that. Oh, and look, we actually did BF out as well. Here. So it was 5 control signals in the last video. And this bottom one, we're not going to talk about because I don't know if I'm actually going to use that all these other control signals. But this one here, well, into E1, they're for bits we haven't built yet. So for the minute, we'll just pretend like they don't exist. In the last video, so the only signals we ain't seen before are, but I changed it to in empty, which is address destination register equal. So how's this work then? Pat EQ, well, which is basically the same as the other destination one before, register equal, except that now and clock enable. BF which in clocks the conveyor belt onto the inbound buffer, and in empty all we need has to be a 0. Is program the EEPROM. Otherwise, these things the 4 outputs we're using just stay as things pop out on the data bus. Now, as you can see, to write the binary all these outputs for the EEPROM We're
Go
going to be
these
using our old
gates.
mate Python.
Except this one here. Let's have a
That
closer
just
look
goes
at
off
this program.
somewhere.
Here, we
But
got
what
all
about the other
outputs.
inputs of the
We're
OR
only really
gates?
interested in these two at
Well,
the moment. And
this one here,
we've got all the
That
inputs.
is attached to the
So
output
what we do
of our
is we
8-bit comparator,
iterate through
which,
every
if you
address
remember,
in the EEPROM,
tells you
and then
whether the
check
address
to
of
see
this
which
board
bits are
is
set and
equal
which
to the
bits aren't.
destination register.
and then finally,
And to make
we
it
stick
easier,
it all in a
we're
file,
calling that
and then
ADEQ.
program our EEPROM. The EEPROM we're going
So
to be using
address
is
equal to
the
destination,
W27C512.
and it's active low.
And we're using
Now
the
we can see
45
that the
nanosecond
input
version.
of both of these
The
OR
reason we're
gates
using these
are attached to the
EEPROMs
same
is
thing.
because, well,
But
one,
what are they
it's
attached
the
to?
fastest one I could
Well,
find.
they're
and
attached to the
two,
output of
we're
our pattern
already using
matcher,
some over
which
here for the
we're
integer
calling
multiplier.
PATEQ.
Right, so human man, you point to the bits.
So
when I say
we
them,
can
all right?
see
So,
that the output
EEPROM
of this OR gate here will only be a 0
will point to it,
if
human man.
DM is a 0, AD is a 0, BF
Yep,
is
that's
a
it.
1, in empty
Then we got
is
this
a
latch
0,
here,
and ADEQ is a 0.
which is human
So
man.
where do all these outputs go?
Yep, right there.
They go
now
into
we've got
this,
inverter
a
and this
4-input
AND
NAND
gate.
gate. So we can
Which are
see that the output
there.
of this NAND gate is a 0 unless
And
one of these inputs changes
there.
to a 0.
Yep, that's it, human
What
man.
is the output of
I
this NAND
suppose you
gate?
better stick some jumper
That
wires
is
and
our
LED
clock
on
enable
there
signal,
so we can test it.
which clocks the data from the conveyor belt into the inbound buffer.
Yeah,
We can
human
see
man.
that we've
lot there.
also got this other NAND gate here, which is going into
Yeah.
an inverter.
Well, what we'll do is the human
So,
man will sort that
this
out, and
signal
then we'll come
here
back when he's done.
is a 1 if
Human
all
man.
these inputs are
You better
1s,
test it, ain't
and
ya?
a 0 if any of these inputs goes to a 0. And what we calling this signal? We're
Right,
calling
now
that
plug it in.
BF out.
Ooh. Oh, human man. You've built it without showing anyone how you built it. I suppose they didn't really miss much.
going on there?
It was just
That's the
you
clock-enabled human
sticking
man.
little black oblongs
With what
into
we
big
got on
white
there.
oblongs. That should be a 0. Yeah, that's it, human man. Well, I suppose we should at least tell them what the chips are and where they are on the schematic. Well, that should be a 1. I'll say them, and the human man will point to them. That should be a 1 here. As well, human man. Why ain't that 1? Is a 748C. Why ain't that 1? That should be 1 as well, human man. Point, human man. Hang on. There you go, human man. There we got the 748C. So 32. Human man is 1, 2, 3, 4. Oh.
You know what we've done, human man?
Yeah,
We
that's
programmed it
human
the
man.
wrong way round.
And then
If you have a look
the
at the human man
748C
scribbles,
20.
you can see he's written the data out as a vector.
There
So
you go,
this
human
is
man.
the first thing in the vector,
then
and this
we've
is the
got the
last
8-bit
thing in the
flip-flop.
vector. But if you have a look at the binary number,
Yep, that's a 748C.
this is actually the last
574.
bit,
And then we've got
and
this
this is the
inverter
first
here.
bit. Suppose that's what you get for being a physicist, isn't it, human man?
And the AND gate down here.
Yeah, we'll just flip them round and we'll reprogram it.
And then,
Right, human
well,
man,
see them things
reprogram
up
it.
there. We ain't going to talk about them yet because they're for bits we ain't made. Right, so, human man, you better stick some jumpers on there and we'll test it. Well, go on, human man, you get all the jumpers. We'll come back when the human man has wired it all up. One's a 1. Human man, you better test it, ain't ya? Now. Right, so clock the flip-flop. So nothing's happened. It works, human man! What have you got there then, human man? You've got DM is a 0. AD is a 0. BF is a 1. In empty is a 0. Oh yeah, human man, you've got ADEQ equals 1. Yeah, change that. Now clock the flip-flop. There you go, human man. Clock enable is on. What about BF out? That's off. Just like it should be. It's all working, human man! Yay!
Right, well, that was virtually unwatchable. Well, anyway, instead of just me deciding which circuit we're going to use, I thought I'd let you lot choose. So, are you yes EEPROM or no EEPROM? Suppose I'll go now. Yeah, see you in the next video when the human man will be building the circuit you choose. I'm going now. Row, 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 bog! Let us watch as Jeff flies majestically in his portable toilet, propelled by nothing less than his own torrential diarrhea.